Good morning, geometry. Today's video deals with section 13-3, looking at special right triangles, and there are two of them. So the essential question is, what do you know about the side lengths and the trig ratios in special right triangles? Now, for this section, I'm going to do it two ways. I'm going to show you what the book does, and then I'm going to go and mostly focus on the three trig ratios that you're familiar with, SOHCAHTOA. If you can understand those three trig ratios, you'll have no problem doing this section. But at the same time, I need to show you what the book shows, because it may be helpful for some of you, and somebody else in the class may understand it better by just using the three trig ratios that we've talked about, the SOHCAHTOAs. All right, so here is the book. The first special right triangle they're focusing on is the isosceles right triangle. Now that one is also shown on page 6 of your HD&Cs. Again, here's a picture of an isosceles right triangle. Once again, an isosceles right triangle has two congruent sides. That means the sides BC and side AC are the same length, and they have two congruent angles. In this case, angle A and angle B are congruent, and as a matter of fact, those two angles are going to be 45 degrees, because if I take the sum of the three interior angles and add them up, they become 180 degrees. That deals with supplementary angles. Again, this is an example of an isosceles right triangle. Now I'll let you guys fill in this information. Some of this stuff is going to be very helpful for you. Letter D deals with the Pythagorean theorem. A squared plus B squared equals C squared. Again, you guys are very familiar with that, so I'm not going to focus too much on that. All right, that is one special right triangle. The other special right triangle deals with an equilateral triangle. Now, an equilateral triangle has three congruent sides and three congruent angles. But in order to make this into a special right triangle, we have to take half of it. So if you look at your picture here, the triangle ABD is a equilateral triangle. That means the three sides are the same length, and the three interior angles, angle A, angle B, angle D, are all the same angles. As a matter of fact, they're going to be 60 degrees, because 60 plus 60 plus 60 is 180. So again, this is just another special right triangle by taking an equilateral triangle and cutting it in half. So you can either focus on triangle ABC, or you can focus on triangle DCB. It does not matter. They're just using that as an example. Okay? That's what they're focusing on. And letter D deals with the Pythagorean theorem of the special right triangle of a half of an equilateral triangle. All right, next page. Now, how do we apply the relationships to special right triangles? This is the part of the book that I'll let you guys study on your own. A couple of things in there you probably can learn from it, but I'm just going to show it to you. I'm really not going to go over it, okay? All right, so let's go to page 712. Now, like I said, you can use what the book tells you in the beginning, but you know what? If you understand the three trig ratios of SOHCAHTOA, you'll have absolutely no problem for anything in chapter 13. SOHCAHTOA, once again, is the three trig ratios of any right triangle, whether it's a special one or not. Again, sine deals with the opposite side divided by the hypotenuse. The cosine of an angle deals with the adjacent side divided by the hypotenuse. The tangent, the TOA is the tangent is the opposite side divided by the adjacent side. So if you have those, you're able to do any of these examples. Now remember, to do these three, You got to go by what they're giving you. Okay, so you got to pay close attention to your triangles. Now, what I've done is did question number 5 on one page and question number 6 on the next page. Now, I did this by color coding so you can see the difference. So here we have triangle LJK. We know that this is a right triangle because we see that this is a right triangle. This is a 90-degree angle. And this is one of those special right triangles that is really a 30, 60, 90, okay? Now what we want to do is we want to find the length of LJ, or in this case, we're going to label it as K. Once again, the angle, okay, angle K, the opposite side is that length of K. And doing the green, you go by what you're given, okay? So if we're going to deal with finding K, we have to focus on angle K. So they gave us angle K and the hypotenuse, which is the side opposite of the triangle, and they gave us the hypotenuse. So that we got to go up to our list. Again, we have our angle, we have our hypotenuse, and we're looking at the opposite side. So we have to use the sine function, okay? Sine is the opposite divided by the hypotenuse. So we do sine of 60 degrees equals the opposite side divided by the hypotenuse. Solving for K, we multiply both sides by 4 radical 3. Again, using your calculator, I have it fired up on the screen. So we go 4 square root of 3 being multiplied by the sine of 60. Hit enter, and that tells me this side K is 6 units. Therefore, we can say the length or the line segment JL is going to be 6. All right, now blue is trying to find the length of the other side, which in this case is length JK. We're going to label it L because it's going to be the side opposite the angle L. So if you look at this problem here, we have to go by what's given. They gave us angle L, which is 30 degrees. They gave us the hypotenuse, which is 4 radical 3. And there's our opposite side, which we don't know what it is. In this case, we're going to have to use sine, because sine is the opposite side divided by the hypotenuse. Remember, you go by what you're given. Now, however, we could have gone, now we know that JL is 6, okay? We could have, okay, if you want, could have used a cosine. Because remember, cosine is the adjacent side, which is K. In this case, would have been 6, divided by the hypotenuse. Okay, that is just another option you may have. But I'm going to focus on the blue. So sine is the opposite side divided by the hypotenuse. So it's the sine of 30 degrees equals the opposite side, which is our unknown side, divided by our hypotenuse, which is 4 radical 3. Multiply both sides by 4 radical 3. Using your calculator, and we get an answer of 3.46. So it's roughly 3.46. Now, that tells us JK, in this case, is 3.46. Now, and since this is in decimal form, Bob is going to have this of 2 radical 3. I have no problem with you writing it down as a decimal, but just make sure that if you look at Bob when they have it as a radical expression, you can go back to Bob and take that radical expression and go 2 radical 3, and you'll see that 2 radical 3 is the same thing as 3.46. And I'm rounding this to the nearest hundredth. Okay? All right, we did number 5. Let's look at number 6. Number 6 is another special right triangle. Okay? But we want to find angle R, because that's all they want is we want to find the unknown length sides. Again, I didn't sign this side right here. I'll show you how to do that one in a minute, okay? So I want to find the hypotenuse. So the hypotenuse in this case is opposite of angle R. And we're given, again, we have three angles here. It does not matter which one to use. And we have another side, which is 2 radical 6. Also, remember, QR is also going to be 2 radical 6 because this is one of those special right triangles. So I use sine in this case. We could have used cosine, but I use sine. So we want to find, it does not matter which angle you use. You can use angle P or angle Q. It doesn't matter. You'll still get the same answer. So we take the sine of 45 degrees. The opposite side is 2 radical 6 divided by the hypotenuse, which is the R. I just labeled it R. Okay. Do your math. Once again, it'll be roughly 6.93. And Bob will have 4 radical 3. Okay. Use your calculator. It'll be no problem. So we have found that the hypotenuse is 2 radical 6. We don't need to find this side right here because we know that this is a special right triangle. These two sides are equal, so that's going to be 2 radical 6. Now, you could have found this side by using Pythagorean theorem if you wanted to. All right, now some other information that we need to do is just for you guys for identification purposes. If you go to the bottom of page 712, and if you take the time, we'll look at example 2a. There's some things I wrote down here, okay? If we look at here, the radical 2 divided by 2 is going to be 0.707. Now, I'm just showing you that in case you deal with, your problem comes as a rational number or a decimal form. And it's the same thing as what I'm just showing you on the screen, okay? All right, go to the next page. Some other information. Letter B. Again, this is a special one where it's 30, 60, 90. We see that one side is a length of 1. Again, the hypotenuse is twice as long as the shorter leg. This is the shorter leg. So the hypotenuse is 2. You can figure that out. The longer side is radical 3, so this is the radical 3. And it's radical 3 times as long as the shorter leg. Okay, I'll throw all that information at you. You can apply that if you like. Down below is taking this diagram, finding the sine of this angle, or again the sine of this given angle, and also the sine of this given angle. And again, I showed you not only the radical expression, but the decimal representation. All right, now that will pretty much cover what section 13-3 is all about. Again, you're more than welcome to use any bit of information in here, but also just at the same time, if you understand SOHCAHTOA, you got the basic understanding of trig functions, okay? All right, so I'm going to wrap it up. We took the time today to look at 2 special right triangles, and we took the time, and it's shown in the book that you can know a little bit about the side lengths and the trig ratios in special right triangles. All right, guys, hopefully this video was very helpful for you. Catch you later.